Hello everyone. This is part 2 of section 1.1. Last time we left off with finding the value of r such that e to the rx was a solution to the differential equation. And now we look at initial value problems, or what we often refer to as just IVPs. So as noted, when we solve a differential equation, we initially derive what we call the general solution, and that involves our constant of integration. And if we are given initial conditions, then we find the particular solution by evaluating that constant. And as we'll see in our examples, this represents a particular curve amongst what we call a family of curves. So here we want to first verify that the given function is a solution, and then determine the value of the constant that satisfies the given initial conditions. So for the function, I'm just going to call it y. You can call it y of x if you like. C e to the 2x. We want to verify it's a solution to this differential equation. And so it looks like we'll only need one derivative, y prime. And c is a constant multiple, so that tags along in the differentiation process. The derivative of e to the 2x is e to the 2x times 2. So therefore 2c e to the 2x. And then we can make our substitution. And we have y prime, which is 2c e to the 2x, equaling 2 times y, which is c e to the 2x. And yes, 2c e to the 2x does equal 2c e to the 2x. So therefore, that equation is verified. So now we want to find the constant of integration, or the constant c. So we use the initial conditions. We'll abbreviate that as IC. And the initial condition is that y of 0 is 3, which means that when x is 0, y is 3. So in our equation, in our solution, y equaling c e to the 2x, we replace y by 3, and we replace x by 0. And that would give us e to the 0, which of course is 1, so therefore c is 3. So then our particular solution is y equaling, to substitute c, which is 3, e to the 2x. So what this represents, if we were to look at the family of curves, the family of curves basically are the exponential functions of the form c e to the 2x. So, for example, this might be what represents the family. All these different graphs. And you could have the opposites actually. If c is negative, be reflections. So all the different graphs that take the form of c e to the 2x. And we basically found the particular solution, which when x was 0, y was 3, so let's say this was the point here, 0, 3. And so we found that particular curve, okay, amongst this family of curves. So, sorry, that's a little blurry there. Okay, so that's the idea. You're not going to have to really worry about the graphing, just the verification, but of course it's nice to see the graphs. Okay, so here's another example. First off, we want to verify. So for the function, again, I'm just going to call it y, c e to the negative x plus x minus 1. Okay, our equation involves just one derivative, y prime. So y prime would be negative c e to the negative x, because the derivative of e to the negative x is e to the negative x times negative 1. Negative 1 being the derivative of the power on the base of e, and then plus the derivative of x is 1, and the derivative of the constant is of negative 1, of course, is 0. So now we make a substitution. We have y prime minus c e to the negative x plus 1. Is that equal to, don't know yet, x minus the y, which was the c e to the negative x plus x minus 1. So recopy the left, distribute the negative, so we have x minus c e to the negative x minus x plus 1. Now the x's cancel. We have minus c e to the negative x plus 1 equals, and these x's are gone, minus c e to the negative x plus 1, and that's verified. So now for the particular solution, the initial conditions, in this case, our y of 0 is 10. So our general solution was c e to the negative x plus x minus 1. So y of 0 equaling 10 means that y is 10 when x is 0. So this will be c e to the negative 0 plus 0. And so therefore c is 11. So then our particular solution is 11 e to the negative x plus x minus 1. Okay, so then for a final example, here, the given function that is a solution. This again is the general solution, y equaling the natural log of the quantity x plus c. Of course, don't forget the formula for the derivative of the natural log of u, which is a fraction, u in the denominator, its derivative du dx in the numerator. So therefore y prime is, log goes away, we get a fraction, x plus c in the denominator, its derivative, term by term, derivative of x is 1, derivative of c is 0, so that's its derivative of just simply 1 in the numerator. Okay, and now make the substitution. Okay, we had e to the y times y prime. Okay, let me actually recopy that. E to the y prime has to equal 1. So now my substitution. So e to the, I have to substitute y, which is the natural log of x plus c, times y prime, which was 1 over x plus c, has to equal 1. Certainly that's not self-evident, but we should recall that whenever we see E and ln hanging around together, there's our inverse properties. Recall that there's two of them. Natural log of e to the x is x, and the second one, e to the natural log of x is x. And so therefore, e to the natural log of x plus c is just x plus c times 1 over x plus c. Is that equal to 1? And yes, treating these x plus c's as binomial quantities, they cancel, replaced by 1's, and 1 equals 1. So it's verified. Alright, I'm going to separate the side work notes here. And now we use the initial conditions to solve for the constant. So y of 0 equaling 0 means that x is 0 and y is 0. The proposed solution, y is the natural log of x plus c. So 0 equals natural log of 0 plus c. So 0 is the natural log of c. And here we have to know the fact that natural log, or the logarithm of any to any base of 1 is 0. But if you want by definition, log base b of n equals x, if and only if b to the x equals n. So that's our formal definition of logarithms. So therefore we could say that this is 0 equaling log base e of c, because natural log has a base of e, of course. And then using the definition, e to the 0 must be c, so c is equal to 1. And so then we get the particular solution, y is the natural log of the quantity x plus 1. Okay, so the final page of notes in section 1.1, we start with mathematical models. And all we have to make sure we know here is that derivatives mean rate of change. Typically we talk about the time rate of change in many practical application problems. So the time rate of change of velocity represents the derivative of velocity with respect to time, and that would be dv dt. And actually note here that the acceleration a is the time rate of change of the velocity, so dv dt. And if we want to write a differential equation, that's a mathematical model of the given situation. So it says the time rate of change of the population p. So this is telling us a derivative, in particular derivative of the population with respect to time, is proportional to, okay, the proportionality symbol is the Greek letter alpha, and then the square root of the population, p. so the square root of p. So this tells us that dp dt is proportional to the square root of p, but then if it's proportional to it, it's just a constant multiple of it, so we say it's equal to, and typically we like to use k, so k times the square root of p. Okay, so in the next example, it tells us the acceleration dv dt, so as we noted here, acceleration is the time rate of change of the velocity. So dv dt, it's already set up for us, proportional to the difference between 90 miles per hour and its velocity. So that statement is just saying 90 minus v. So we could write that dv dt is proportional to 90 minus v, and then as an equation, you could actually skip the proportionality portion if you want, and just say that, go right to the equation. It's going to be k times that binomial quantity, 90 minus v. Okay, and then we have something a little more interesting here. City has a fixed population p, time rate of change of the number n. So that would be dn dt, where n represents those persons infected with a contagious disease, is proportional to the product of the number who have the disease and the number that do not. So here, what we have to realize is that if n represents the number of people that have the disease, then, and p is the total population, you either have the disease or you don't. So if n people have the disease, then p minus n people do not have the disease. So therefore, the time rate of change of the number of people that have it, dn dt, is proportional to the product of n and p minus n. So therefore we could write that dn dt as an equation is equal to k times n times the binomial quantity p minus n. Okay, and the final concept in this section is just to kind of get us used to the concept of solving a differential equation. We typically will have methods. We're not going to just be guessing, but here we're going to use our knowledge of derivatives to make some educated guesses and check to see if we're correct. So we want to find a solution. So we're looking for the function y. A solution to the differential equation is the function y that satisfies the differential equation. So here we're looking for a function such that its derivative is equal to that function. And one of the things that we should know is that there's a really special function out there whose derivative is itself, and that's the exponential function e to the x. So if I guess y equals e to the x, y prime is also e to the x. So if I make a substitution to verify into y prime equaling y, we get e to the x equals e to the x, and it's verified. Okay, now in the second example, we're looking for a function y such that x times its derivative plus that function gives us 3x squared. Well, if we're adding, let's say we don't know what this xy prime is, but we know the y does in fact have to be of degree 2. So it has to be something involving x squared, because to take this plus something to get 3x squared, this y would have to involve an x squared. So let me make my guess, and then we'll modify if necessary, to be just x squared. And then y prime equals 2x, and if we substitute, okay, I'll recopy the equation, xy prime plus y equals 3x squared. We have x times 2x plus x squared. Is that equal to 3x squared? And we get 2x squared plus x squared. And now it's pretty obvious, but just take one more line to state it. 3x squared equals 3x squared. And it's verified. So therefore x squared is the solution. Is a solution, I should say. Okay, and then E, you're going to notice, pops up quite a bit in differential equations. And here, if we take y prime plus y, we have to get e to the x. I'm going to have to make a guess and say it's e to the x. But if I guess at e to the x here, y prime is e to the x. I'll make my substitution below, because it actually doesn't work, because y prime plus y equaling e to the x. If y prime is e to the x and y is e to the x, that's not true. 2e to the x is not equal to e to the x. So therefore we'll modify the guess. We can pretty much assure we're on the right track, except we basically ended up with twice as much as what we need. So a good guess at this point would be 1/2 e to the x. And then y prime is 1/2 e to the x. And upon substitution, we'd have 1/2 e to the x plus 1/2 e to the x. Is that equal to e to the x? And yes, e to the x equals e to the x. So therefore it's verified. Right, so that's the end of section 1.1. So we'll see you when you're ready for 1.2.